All right, good morning, everyone. Sorry I can't be there with you. I just wanted to make a video going back over what we know about translations, say that again. What we know about types of transformations. So types of transformations that we are talking about here are broken up into either rigid or non-rigid, right? So our rigid types of transformations. Rigid means that the size and shape does not change. So I could take any given line, let's say this was a line on a graph, and I could rotate it, I could reflect it, I could translate it, move it over and move it up, but I'm not going to make it any different length. Rigid means, again, it stays the same size. It just can rotate, reflect, or translate. Okay? So rigid, that means we have translations. The easy word to remember a translation is called a slide. That means that it's moving right or left, up or down, right? So translation, we write it in the form of the whole x plus h, y plus k, this right here. And what this means, what we're looking at, this plus h is how I'm moving on the graph, right or left. The plus k then tells me how I'm moving on the graph, up or down. Okay, so for my original xy point, the plus h says, oh, your x went to the right. The plus k says, oh, you went up too. Okay, so the plus h and the plus k part is telling me exactly how this is translating on a graph. Left or right, up or down. Again, x goes left, right, y goes up, down, right? We also have what we know as rotations. And with rotations, that's a type of turn, okay? It's like a type of turn. If you've ever heard of rotating your tires, right? They don't just take your tires off and roll them down the street. Okay, yeah, I rotated them. No, what they do is the tires stay put and they rotate them about a single point. They rotate it about a solitary, doesn't move point, a point of rotation, right? So it's almost like there's an imaginary string. So if you're going to be rotating a shape, right, say a triangle in a graph, then there is a point that it's rotated about. So the triangle might be right over here. There's a little imaginary string, and that triangle gets rotated around that little string or that little point. Typically, the point that you all are rotating about is called the origin, which is your 0, 0. So most of you, when you guys are doing rotating, actually pretty much everyone, it's the point is at the center of the graph. Wherever your shape is, there's sort of an imaginary line and it's getting rotated. It's hard for me to draw a circle like this. Rotated right around the origin here. Getting rotated right around the origin. Just like that. All right. We've done this right in depth, you guys, last week. We know that there are rules for rotations, and our rules for rotations means I can go 90 degrees clockwise, I can go 90 degrees counterclockwise, I can go 180 degrees clockwise or counterclockwise because you end up in the same spot, and then I can go 270 degrees clockwise or 270 degrees counterclockwise. I want to show you again just to remind you, right? If I think of it in terms of a clock, because a clock really is a good representation of a coordinate plane. So I'm going to make a really big graph behind it so you guys can understand. A clock really is just like the coordinate plane. There's my XY, the clock is right there in the middle. So what I know is that a clock, just like a coordinate plane, is 360 degrees. Well, 360 divided by 4 means each of these little quadrants is 90 degrees. So on a graph, each of the little boxes is a 90-degree turn. So clockwise means you go to the right. So if I'm starting right here, then this would be my first 90 degrees because it's my first box, right? So there's my first 90 degrees. The next one would be another 90. Well, 90 plus 90 is 180 degrees. That would go from here to here. The next one from here to here, another 90 would be 270 degrees. And going all the way back to the beginning, this would be a full 360 degrees. All right? On a clock, clocks are literally just from the coordinate plane divided. Well, 90 degrees on a clock, this is 12 o'clock, this would be 12:15. So these are 15-minute increments, 15 minutes and 15 minutes. Then here would be my 30 minutes, here would be my 45 minutes, and this would be my 1 whole hour. Okay? What we know. So I'm showing you this because I want to explain that 90 degrees clockwise is the exact same as 270 degrees counterclockwise. Clockwise means to the right, counterclockwise means to the left. So if I want to go 90 degrees, right? If I want to go 90 degrees, that means I'm going one turn to the right, 90 degrees. If I want to go 270 degrees counterclockwise, I start at 0. 270 is 3 of the boxes. 90, 90, 90. Look, you end up in the same spot. 90 degrees clockwise is the same as 270 degrees counterclockwise. That also means that 90 degrees counterclockwise is the same as 270 degrees clockwise. Why am I telling you that? Because what it does is gives you two rules that are identical, so you don't have as much to learn. So let's see here. Here's your rules of rotations. Notice, my 90 degrees clockwise is the same as my 270 degrees counterclockwise. What my original point was gets changed to where the y comes to the front and the x goes to the back, and you change its sign. Same thing, y came to the front, x went to the back and changed its sign. I can also look at my 90 degrees counterclockwise, and what changed? The orientation, meaning the y came to the front, x to the back. This time the y sign changed. For 270 clockwise, again, orientation changed. X went to the back, y came to the front, and the sign of the y changed. 270 degrees, whether it's clockwise or counterclockwise, you end up in the same exact place. So the orientation changes and the sign changes. Oh, I'm sorry, scratch that. Orientation doesn't change. It still stays in the form of XY, just both signs change. So there's my rules for rotation. Here are my rules for reflections. For when I reflect over the y-axis, we can see our changes. X-axis, y is equal to x, y is equal to negative x, and the origin. Series of rules. What I like about rules is you just have to plug into them, and it's easy to go. You just plug and chug is what it's called. Plug it in, and you get moving. Okay? So now moving on to reflections. So here's what we know, right, about our rotations. We know our translations, translation slides, rotation turns. All of those are types of rigid transformations. Transformations are just changes, right? Transformers, they change. That's where the word comes from. So now when we talk about reflections, what we have to remember is what we know about a graph, okay? On a graph, the horizontal line, this is my x-axis. What goes left to right is my x-axis. And what goes up and down is my y-axis. So if I'm telling you that I want to reflect over the y-axis, well, that means I want to reflect over this vertical line. So if you took a piece of paper and you fold it in half the long way, when you reflect over the y, that means you're reflecting going left and right, because this is my y-axis, so it has to fold over the y. Okay? Say that again. When I want to reflect over the y-axis, that means I want to fold over, this is the line you're folding over. So I'd have to go left and right to fold over it. That's reflecting over the y-axis. If I want to reflect over the x-axis, then that means the x-axis, this one, when you reflect over x, is going to be going up or down. It's an easy way to kind of work smarter, not harder, right? If I say reflect over the x, you should know the shape is going to be going up or down. If I'm telling you to reflect over the y, it should be going right or left. It's like folding papers, all right? That's what we need to know there. Reflecting over y is x, they go like this or they go like this. And reflecting over the origin just means that it's kind of split in half there. And there's rules, and we're going to apply the rules. So that's what we're going to go ahead and look at. I want to show you an example real quick of how to do some reflections, because that's where we are now. So let me pull up the example. Okay. JKL, I'm reflecting a triangle, and this is at 1, 1, this is at 3, 4, and this is at 4, 2. Okay. Alrighty, sorry about that. Okay, so this is what we're going to work on. I have a shape on a coordinate plane, and I want to reflect it over the x-axis. I want to reflect it over the x-axis, reflections. So I then want to come here and I want to look at my rules, and when I reflect over the x-axis, what it tells me is that my original point, every one of my points is an xy, so my original coordinate changes from my original coordinate to positive x, negative y. Sorry, a little bit of that got erased there. So it's a positive x and a negative y. Well, this is easy because what that means is I don't have to switch, I don't have to flip them. I just rewrite my points and I make all my y's the opposite sign. That's all it means. I rewrite the points and then I just make all my y's opposite. Why? Because flipping over the x-axis, reflecting, means if it was in the bottom, it's going to the top, and if it's going from the top, it's going to the bottom. Well, what makes something go up or down is the y. That is the reason we change the y coordinate when we're reflecting over the x. So how do we do this? Well, what we do and what I teach all of you to do is first you list your points, okay? So I'm going to go ahead and list my points. I have J, K, and L. And I'm going to write J is 1, 1, K is 3, 4, and L is 4, 2. And I want to apply my rule of reflecting over the x-axis, which means now I'm going to do x, negative y's. Boom, wrote them all out. Now I'm going to write my new points. So I have space for my new points here, 1, 2, and 3. All right? So that means nothing changes. I rewrite it if the x is y. Because x comma y, it still is as xy. So it's 1, 1, 3, 4, and 4, 2. But the only thing that's different from the original xy to the new is that the y sign changes. So I'm going to just simply go to each of my y coordinates and change the sign. Well, positive 1 becomes a negative 1. Positive 4 becomes a negative 4. Positive 2 becomes a negative 2. Boom, I got all my new points. And then all I have to do is graph them. Since it's up here, since it's up in the first coordinate, I guarantee you when I flip it, it's going to be right down here in this fourth coordinate because I have to fold it over the x-axis line. So I would regraph it and it would be right down here. And that is how you reflect over coordinates. Now, this is how you reflect when we're doing translations. Rotations, reflections, i.e. reflections today, types of transformations which are rigid. The size will not change. You're either going to flip it, reflections, rotate it, turn it, or slide it left, right, up, and down. That's all we're doing today. So what we're working on, you're also going to do a review so that you can be prepared for your assessment.